Warm welcome to everyone. Today, our seminar is on classification using hyperdimensional computing. We are Group 5, Meenakshi, Dimitra, and Georgius. So, let's start with Introduction to Hyperdimensional Computing. Can we go to next slide? HD computing draws inspiration from human brain's ability to process information in high-dimensional spaces. It uses vector to represent possible brain state. HD computing utilizes a unique data type called hypervectors, whose dimensions are typically in 10,000s. It finds its application in language classification, image classification, speech recognition, and face detection. Also, it has many advantages over classical computing, like it has fast learning ability, high energy efficiency, and acceptable accuracy. Can we go to next slide? Comparing classical computing and HD computing in terms of data representation, data transformation, accuracy. In classical computing, data representation is usually in form of 2 bits, that is 0 and 1, with lower dimensionality, and it is less tolerant to errors. In data transformation, it involves operations like addition, subtraction, multiplication, and division, and it has higher accuracy where the models are very complex. It has longer training times and high energy consumption. While in HD computing, it uses high dimensional data called vectors for data representation. They are highly robust to noise and errors due to their high dimensionality. Typically, it uses 3 basic operations: multiplication, addition, and permutation. And they are simple and fast networks to train. They are highly energy efficient and with acceptable but typically low accuracy. Next slide, please. Data representation in HD computing is basically in type of hypervectors, and hypervectors can be bit, integer, real numbers, or complex numbers. Hypervectors are basically of 2 types: binary hypervectors and non-binary hypervectors. Binary hypervectors consist of zeros and ones, and binary hypervectors are more hardware friendly and they have high computational efficiency. Whereas non-binary hypervectors can be bipolar and integer hypervectors. They have high accuracy and they are suitable for more complex computational tasks. Choice of hypervector will depend on the requirement of the task, balancing between efficiency and accuracy. Next slide, please. Similarity measurement. Typically used similarity measurement are cosine similarity, Hamming distance, overlap, and dot product. They are used to measure similarity between 2 hypervectors in HD algorithms. Cosine similarity is basically used for non-binary hypervector. In cosine similarity, it measures angle between 2 hypervectors, focusing on orientation of the hypervector rather than magnitude. If cosine similarity between 2 hypervectors is equal to 1, it indicates that hypervectors are identical. And when cosine similarity between 2 hypervectors is 0, it indicates that hypervectors are dissimilar or orthogonal to each other. Orthogonal hypervectors are considered as dissimilar hypervectors, where a 90-degree angle between a hypervector indicates that there is no similarity. Usually, randomly generated hypervectors are nearly orthogonal. Now, let's see about Hamming distance. It is usually used for binary hypervectors. It measures similarity based on the number of differing bits. When Hamming distance between 2 vectors is 0, it indicates that hypervectors are identical. And when Hamming distance between 2 hypervectors is 0.5, it means they are dissimilar. Now, let's look how they do data transformation. Next slide. So basically, hypervector uses addition, multiplication, and permutation operation to on both binary and non-binary hypervectors to do data transformation. Usually, if we take like input hypervectors like x1, x2, xn, and when we do pointwise addition on them, we get a resultant hypervector z, which is similar to the hypervectors x1, x2, x3, etc. And this operation is usually called bundling operation. Multiplication. Multiplication is like forming association between hypervectors. Like if we have two hypervectors A and B, and it's like XORing operation. So it binds two hypervectors together, and X is approximately orthogonal to both A and B. Next is permutation operation. It generates sequence or ordered pairs. Now Dimitra will be continuing.
Hello, everyone. This is the system diagram of for the classification tasks using HD computing. During the learning phase, the encoder employs randomly generated hypervectors to map the training data into HD space. Then a total of k-class hypervectors are trained and stored in the associative memory. During the inference phase, the encoder generates the query hypervector for each test data. Then the similarity check is conducted in the associative memory between the query hypervector and every retrained class hypervector. The label with the closest distance is returned. The encoding the encoding process used in HD algorithms is somewhat similar to extraction of features. The two encoding methods commonly used include record-based encoding and n-gram-based encoding. We have encountered n-gram-based encoding in the labs. The learning and the classification process can be benchmarked using accuracy and efficiency as metrics. The encoding methods impact accuracy, and the choice of method can enhance the performance. Binary hypervectors are less accurate but more hardware efficient, while iterative retraining can improve accuracy over single pass training methods. Concerning efficiency, the algorithm improvements and hardware optimization are key aspects for efficiency. The dimension reduction and binarization can conserve resources and speed up computation. And emerging technologies like SCN, FETs, and RAM shows promise for HD computing, offering speed and energy efficiency. Some of the applications of HD classification concern letters for text recognition, signals, and images. We will see some of the use cases that were examined in the paper. One of them is the European language recognition using HD computing. This is exactly the case we encountered in one of the labs, where we have the encoding module and the search module, and we have the trigrams, and we were able to distinguish which language was in the text, in which language was the text written. Considering signals, we have HD classification methods for speech recognition, where voice signals are transformed to the frequency domain and the resulting information is mapped into random hypervectors. The paper that examines and proposes voice HD was combined with a small neural network right here, and it was found to have improved the classification accuracy and significantly faster training and testing speeds with compared to a pure neural network. Another application was to detect seizures using HD computing, where a LiLAP algorithm was proposed. This algorithm employs local binary pattern codes for feature extraction from intracranial electroencephalogram signals. The algorithm captures the statistics of time-varying LBP codes for all electrodes, demonstrating superior energy efficiency compared to other machine learning methods like SVM. The algorithm involves encoding the samples into 6-bit LBP codes, creating composite hypervectors for each electrode and deploying prototype hypervectors for interictal and ictal states. That's the states when the person has a seizure and between seizures, achieving effective seizure detection with a post-processing mechanism for generating seizure alarms. Another application is quantization in HD computing. This application converts trained non-binary hypervectors to binary or ternary models, and it compensates for the accuracy degradation caused by floating point models, and it employs a retraining approach with predefined iterations. The similarity check shifts from cosine metric non-binary model to Hamming distance or dot product. In comparison with existing binarized HD computing, QuantHD demonstrates an average improvement of 17.2% accuracy with a similar computational cost. George, can you continue?
Yes, hello. So another useful application for HD computing is that of model compression. So what we mean about that is that HD computing can be used as an alternative for machine learning problems, particularly when they need to be run on devices with limited power of capacity, computational capacity. The HD computing method is proposed to compress the model size of high-dimensional hypervectors while minimizing the loss of accuracy. By employing a compressed architecture, HD computing utilizes orthogonal hypervectors generated through Hadamard method, achieving a reduction in model by approximately 69%, while maintaining some high accuracy that is lower than, let's say, the more demanding, computationally demanding algorithms, but yet quite comparable. This approach proves that these kind of methods can be used in IoT devices, which don't have normally high computational capacity, and demonstrate significant energy efficiency compared to normal applications that are running more powerful processors. This is particularly useful in applications such as recognition, gesture, activity recognition, gesture recognition, and valve monitoring. Next slide, please. So another application of HD classification is the case of adaptive efficient training, which is used to address the issue of low accuracy when we have a single pass training through HD classification methods. The adapt HD method involves using a binary iterative retraining processes where initial training is conducted using binary hypervectors to generate a non-binary class hypervector. The class hypervector are retrained by considering the similarity between each trained class and the training hypervector. The model then is updated based on the specified conditions, and after convergence, only the final trained model is binarized for inference. The adapt HD method employs adaptive strategies, including iteration-dependent, data-dependent, and hybrid approaches, adjusting the learning rate alpha to achieve improved accuracy and convergence. Some evaluations that have demonstrated that the hybrid adapt HD methods can achieve almost 7 times X speed up and approximately 6 times X energy efficiency improvements comparing to existing high HD algorithms. Next slide, please. Another useful application of HD classification is that of binary framework. The binary framework of HD computing, also known as BEMs, is used to address the trade-off between the accuracy and the energy efficiency we discussed earlier. Whereas in this approach, BinH employs a binary hypervectors, leveraging the hardware-friendly Hamming distance metric in 3 main blocks: encoding, associative search, and counter modules. Evaluation results over the practical application demonstrate that the BinHD achieves more than 12x and 6x energy efficiency speed up improvements during the process, as well as during the training process, as well as almost 14 times X and almost 10 times X during inference. Compared to the state-of-the-art edge computing that have similar classification accuracy. Also, another application of HD classification is the hyper HD computing for semi-supervised learning. HD computing for semi-supervised learning is addressed by the semi-HD framework, which is a training approach for semi-supervised scenarios with a small portion of labeled data and large portion of unlabeled data. So what this framework involves is encoding all data points into the high dimensional space we discussed earlier, starting the training with the labeled data that are available to generate class hypervectors, predicting the class of unlabeled data, as discussed by the previous slides, based on similarity with class hypervectors. And then iteratively expanding the labeled data as new knowledge is produced. The training stops when the accuracy is stabilized and everything is converged. And the model is then used for inference by comparing the similarity of the test data with the training model. The evaluation of results of this framework shows improvement in supervised HD classification by almost 10%, more than 10% on average with FPGA implementation, offering approximately 7 times faster speed and 12 times energy efficiency compared to the best CPU implementation. Next slide, please. Also, as we have seen, the HD classification can be used for character recognition, in which approach HD classification for character recognition employs HD computing for characters that are encoded in represented in a 7 times 5 pixel input image, where each pixel is encoded to a binary hypervector, and based on a hollow GN encoding, a hollow hyperdimensional vector is generated using a majority rule. The system performs well for character recognition, achieving comparable accuracy with reduced dimensionality. an increased input image size while showing robustness against noise. The system achieves average accuracy of approximately 90% with a 50% distortion. Future directions that have been discussed for the direction that HD computing could take, as it is still in its early stages, include exploring more cognitive tasks beyond classification, addressing challenges in feature extraction and encoding for signal matches, developing new hardware-friendly similarity measurements, investigating the use of multiple classes hypervector for improved representation, implementing strategies like retraining for accuracy improvement, exploring hardware acceleration for efficient manipulation of large amounts of hypervectors, considering the trade-offs between dense and sparse approaches based on each application scenario, developing a general purpose hyperdimensional computing processor, and finally researching hybrid systems that combine hyperdimensional computing with conventional machine learning. Finally, to discuss the connection with the main paper that referred this research paper, is that the main paper we have presented here it presents an overview of the use of hyperdimensional computing to solve machine learning classification tasks. While it was not the main paper's coverage, it serves as a reference for exploring areas where hyperdimensional computing has been successfully employed. Thank you. We are ready for questions.